Okay, we are going to find out how do we work out the pH of solutions of strong acids and strong alkalis. Okay, so we're going to use these two equations here. Well, we're going to use this equation. First of all, pH is equal to the minus log of the hydrogen ion concentration. And in later problems, when we do it the other way around, we need to know that you can work out the hydrogen ion concentration from the pH. H plus is equal to the power of 10 to the power of minus pH. Okay, so that's right. First of all, we've got a pH. We find the pH of a solution of HCl of concentration 0.15 moles per decimeter cubed. Right, now HCl is a strong acid, so that means if you put HCl into solution, all of it will dissociate. 100% of it will dissociate into the ions. Okay, and that's really H3O plus. Right, so that means if we have a concentration of that of 0.1 mole per decimeter cubed, the hydrogen, it was going to give 0.1 mole per decimeter cubed of hydrogen ions in solution. So the pH is pretty easy to work out. The pH is equal to, well, so it's not 0.1, it's 0.15, isn't it, in the question? So I'll just change that. 0.15. 0.15. So yeah, hydrogen ion concentration is equal to 0.15 moles per decimeter cubed. So pH is the minus log of 0.15. So do that in the calculator. The answer is 0.82. 0.82. It should go to 2 decimal places always, so that's the answer there. pH is 0.82. Right, that's pretty easy. Now let's have a look think about if you doing it with sulfuric acid this time. Now it's a little bit different here because sulfuric acid is a strong acid, yeah, but sulfuric acid, 1 mole of sulfuric acid when it dissociates is going to give you 2 moles of H plus ions. It's a dibasic acid, isn't it? So what's the concentration of H2S? So 4 there is, the concentration is 0.8 moles per decimeter cubed. So the concentration of the hydrogen ions is going to be double that. Okay, so that's 0.8, that's 0.36, isn't it? So pH is equal to minus log of 0.36, which is 0.44. 0.44 is it's 2 decimal places is the pH of the sulfuric acid. So yeah, sulfuric acid, the same concentration of hydrochloric acid, you're going to have double the hydrogen ion concentration, so the pH is always going to be lower. Let's now have a look at this acid, right? Right, find the pH of a solution of ethanoic acid of concentration. Right, so ethanoic acid is not a strong acid. I'll write it down here. CH3, COH. Now it's an equilibrium reaction. CH3, COO minus, and H plus. Now the concentration of this stuff is 0.15 mole per decimeter cubed, but we don't know the concentration of H plus. We don't know because we don't know how much of this dissociates. We don't know. So you cannot do that. We can't do that yet. We'll find out later on how to do that, but you cannot do it that way because ethanoic acid is a weak acid. And so you don't know what proportion of it is going to dissociate. Right, let's do the let's do one of these backwards, shall we? Okay, so go back up to the top, and so we've got our equation. We're going to use this equation this time, yeah, this bottom one. Right, so the question could say, let's have a think. Right, find the concentration, let's say. So a solution of HCl has a pH of 1.87. Find the concentration of the HCl in moles per decimeter cubed. So how are we going to do that? Right, we know the H plus concentration from this equation, yeah? H plus concentration is equal to 10 to the power of pH minus pH, which is equal to 10 to the power of minus 1.87, which is, so you do your shift log button on your calculator, and there's a little yellow thing above the shift, so it's 10 to the power of whatever. So shift log minus 1.87 gives us, to three significant figures, 0.0135 moles per decimeter cubed. There's the answer. Well, not quite the answer, the hydrogenite concentration. And we just need to remember that 1 mole of HCl gives 1 mole of H plus ions. So we can say there, the concentration of HCl is the same as the concentration of H plus, which is equal to 0.0135 moles per decimeter cubed. Let's do that with sulfuric acid this time, okay? So I'm going to get rid of this. Right, I'm going to change that to sulfuric acid. H2SO4. I'm going to change the concentration, change the pH. Let's put it 1.3 or something, yeah. 1.30 should give us a 2dP. 1.30, and find the concentration of the sulfuric acid in moles per decimeter cubed. So what we got there then? Well, let's find out the hydrogen concentration first of all. H plus, using this bottom green equation, yeah, again is 10 to the power of minus pH, 10 to the power of minus 1.3, which is equal to 0.05. Right, let's give it 3 sig figs. 0.0501 moles per decimeter cubed. Now we have to be a bit careful there because 1 mole of sulfuric gives us 2 moles of hydrogen ions in solution. So therefore, the concentration of H2SO4 is equal to the concentration of the hydrogen ions divided by 2. So that's going to be 0.01501 over 2, which is equal to, I left the number in my calculator, 3 sig figs is 0.0251, okay? 0.0251 moles per decimeter cubed. Right, let's get rid of that because we don't want that anymore, do we? Okay, so there's the answer to that one. Okay, we've done acids. Now let's move on to strong alkalis. Okay, now strong alkalis. What are strong alkalis? Right, what we need to do really, we're talking about strong alkalis. We're talking about hydroxides, soluble hydroxides. Now, the only soluble hydroxides we really come across are the group 1 hydroxide. Let's forget about lithium because we don't really do that much, but certainly sodium hydroxide, that's the most common one, potassium hydroxide. And then we also have to be a little bit careful. You might get a group 2 hydroxide. Some of them are soluble, aren't they? So let's say barium hydroxide, BaOH twice. Okay, now you can see that's going to be a bit different because there's 2 OH minus ions for every 1 mole of barium hydroxide. Now we also need another equation to be able to do these. We need the Kw expression. Kw is equal to H plus OH minus, and we're going to take it to be 1 times 10 to the minus 14 because we're doing this at 298 Kelvin. Okay, and you're always given the value of Kw. You don't have to remember it, but you probably will remember it anyway. So let's do one. Find pH of NaOH of concentration 0.1 0.12 moles per decimeter cubed. Now, so these are all soluble. So if the concentration of NaOH is equal to 0.112, the concentration of the OH minus ions is going to be the same, 0.112. Now we need to work out pH, so we're going to have to do something with this. And pH, you need to work out the hydrogen ion concentration. So we've rearranged this equation, and we're going to get H plus is equal to Kw over OH minus concentration. We know the value of Kw, which is 1 times 10 to the minus 14, divided by the OH minus concentration, which is 0.112. Do that in the calculator. Sorry. That's 8.92 times 10 to the minus 14 moles per decimeter cubed. So now we have to find out the pH. So we're going to minus log this number here. Move those out of the way. So pH minus log of 8.92 times 10 to the minus 14. That is equal to 13.05 to 2 dP. So pretty alkaline. That is our answer there. Should we do one with barium? Let's do one with barium hydroxide, and we have to be careful there because, okay, we have got 2 moles of that there. Okay, so I'm going to get rid of all of this. And let's change that to barium hydroxide there. BaOH twice. We'll change the concentration. Let's make that 0.215. Okay, so we're going to say 1 mole of, I'm doing a different color, I think, doing red. 1 mole of barium hydroxide gives 2 moles of OH minus ions. So therefore the concentration of OH minus in this solution is going to be 2 times 0.215, which is equal to 0.430. Okay, now we have to find out H plus concentration from that using the Kw thing again. Let's do that. So we get H plus concentration is equal to, H plus is equal to the concentration of Kw divided by OH minus, which is equal to 1 times 10 to the minus 14 over 0.430. Do that. Uh, 2.32 times 10 to the minus 14. Then we have to take a minus log of that to get the pH. pH is equal to the minus log of 2.32 times 10 to the minus 14, which is equal to 13.63 to 2 decimal places. Okay, this video is going on a bit, but let's just do the opposite of that, shall we now? Let's do the other way around. So what I mean by that is, let's get rid of all of this. Right, we're going to say a sodium hydroxide solution. A sodium hydroxide solution has a pH of 12.62. Calculate the concentration. Right, what do we know here then? Right, we know we're going to have to use this equation, not this one, we're going to have to use this one here. H plus, find out the pH find out the H plus from the pH. All right, let's do that. So we're going to have H plus concentration in this sodium hydroxide solution. It's going to be very low because it's an alkaline solution, but there'll still be some there. Is 10 to the power of minus 12.62, which is equal to 2.40. Okay, but I'll leave the number in the calculator to deplete to 36 figs times 10 to the minus 13. Okay, so now we need to work out the concentration of sodium hydroxide. So we've got to find out the OH minus concentration from the H plus. Well, we're going to use this equation here, aren't we? OH minus is equal to Kw over H plus. So that's 1 times 10 to the minus 14 over this 2.4 times 10 to the minus 13. That's equal to, so I've left a number in my calculator, so don't worry about the rounding up. Right, that's equal to 0.0417 moles per decimeter cubed. Now that's the OH minus concentration, and we know that 1 mole of what's that?
Delivery to Mr. Davies.
So 1 mole of that is 1 mole of OH minus comes from 1 mole of NaOH. So the concentration of the NaOH is the same. It's equal to 0.0417 moles per decimeter cubed. So let's call that a day there.